Hello everyone, good afternoon, and welcome to my talk about automated vulnerability hunting in SMM. First let me just introduce myself. So my name is Assaf. Currently I'm a security researcher at SentinelOne. Also working with me on this project is my good friend and colleague Itai, who unfortunately couldn't be here today due to some prior commitments. So he won't be with us physically, but I do hope he will be with us in his spirit. So the talk is basically divided into three parts. In the first one, we will do a quick recap of what SMM is and how it operates under the hood. Then we will move on to the second part where we describe some common bug classes and attacks against SMM code. And we will conclude by presenting a small tool we wrote that helps you automatically detect some of these bug classes. So let's start with SMM. SMM stands for System Management Mode. It's one of the operating modes found in every Intel-compatible CPU, alongside the more familiar modes such as real mode, protected mode, long mode, and so on. And SMM was designed to be used exclusively by the firmware to handle some low-level operations. So typical examples would include things such as power management, thermal control, emulating legacy devices, or basically any other piece of code the OEM wants to put into the box. SMM has been with us for over than 30 years, so it's definitely not a new piece of technology. And at the beginning it was pretty modest, but over time it has grown in significance, simply because OEMs started shifting more and more functionality into it. And so the end result is that a typical firmware image nowadays, on a modern laptop for example, contains a magnitude of dozens of different executable images that all execute in this mode. Now, SMM code runs from its own isolated address space, known as System Management RAM, or SMRAM for short. This is just a region of physical memory where the SMM code and data lives. And if you want to know the exact address range SMRAM spans, you can do it quite easily, simply by reading a bunch of registers called SMM range registers, or SMRRs for short. And alternatively, you can use a tool called ChipSec that lets you read and validate certain firmware level settings on your machine that also gives you the same information. Now, one of the main features of SMRAM is that it can be closed and locked by the hardware in order to isolate SMM from the outside world. So when SMRAM is closed and locked, only code already running in SMM can access SMRAM contents. So put it into other words, any attempt to access SMRAM from a non-SMM context would fail or be remapped by the hardware or something like that. And that restriction even applies to some highly privileged components, including the OS kernel, the hypervisor, or even I/O devices that are capable of doing DMA. Now, SMM code is triggered in response to what is known as a System Management Interrupt, or SMI for short. These are high priority interrupts, so they can preempt basically almost any code that runs on the system. And when such an SMI is fired, control is transferred into a dedicated routine called the SMI handler. So generally speaking, there is only one such handler, but during boot time, the firmware can register additional sub-handlers in order to handle particular events. Now, SMIs come in several flavors. First, we have the distinction between hardware SMIs and software SMIs. So hardware SMIs are mostly asynchronous events that are generated by a plethora of devices all connected to the system. So typical examples would be things like the USB bus, power buttons, or basically any other device that is transitioning between different sleep states. Software SMIs, on the other hand, are mostly synchronous events that are generated intentionally by software. And the most common use case is for non-SMM code to request certain services from code already running in SMM. So basically we can think of these as the SMM equivalent of a system call. Now, in the UEFI specification, software SMIs can be again divided into two subtypes. First, we have the legacy software SMIs that I won't talk a lot about them. And then we have the other subtype, which I chose to call CommBuffer SMIs. And these will be the focal point of this talk. Now, in order to register CommBuffer SMIs, UEFI code can call a service called SMI handler register. And each handler gets assigned a unique GUI that lets us easily reference it and locate it afterwards. Now, let's talk a bit about how these SMIs are invoked. So in UEFI, all the communication, all the interaction between non-SMM code and SMM code is mediated via a dedicated protocol called the EFI SMM communication protocol. So that means any code that wants to trigger these SMIs must first retrieve an instance of that protocol. Afterwards, the code is allocating what is known as a communication buffer, or CommBuffer for short. This is just a region of physical memory that will be used in order to pass arguments to the SMI handler and get back some of the results. Now, the contents of the communication buffer can be broadly divided into two categories. So first, we have a fixed size header that specifies the GUID of the handler we want to invoke, as well as the length of the data that follows. And afterwards, there is a variable size structure which holds the arguments that are tied to the particular type of SMI we are invoking. So after the contents of the communication buffer were prepared this way, the code calls the communicate method of the SMM communication protocol. And this method call is eventually resolved into a function called SMM communication communicate. SMM communication communicate basically does two things. So first, it places the pointer to the CommBuffer, as well as its size in their respective fields in a global structure called GSMM core private. This structure is shared between SMM code and non-SMM code, and therefore we can use it in order to pass information between the two modes. And afterwards, it calls the trigger method of the SMM control protocol in order to actually generate the SMI. So under the hood, the trigger method does little more than simply write to the two IO ports B3 and B2. So that begs the question, what is so magical about these two IO ports? And as it turns out, these two IO ports belong to the IO range of a small component called the APM controller, or APMC for short. Port B2 is actually a control register that when written by software is also going to assert the SMI pin of the CPU. So basically this is the basic building block software uses in order to trigger SMIs in a controlled manner. So after the transition to SMM takes place, a function called the SMM entry point is called. And this function takes the pointer to the CommBuffer and its size from the GSMM core private structure. And then it uses the GUID found at the beginning of the CommBuffer in order to locate the handler we wish to invoke. In the last phase, the SMI handler finally gets called, and now it can freely access the contents of the communication buffer. Now, an important thing to notice is that while the handler itself runs in SMM and located in SMRAM, the contents of the communication buffer themselves are outside of SMRAM. So that's a point we will get back to. Okay, so now let's move on to the second part where we describe some practical attacks against SMM. But first, let's give some motivation for doing this in the first place. So the main reason of attacking SMM is that it's considered to be a highly privileged operating mode of the CPU. So in the Intel realm, we like to think of privileges in terms of numbered rings, where a lower ring number indicates higher privileges. And according to this convention, you can think of SMM as ring -2. So that makes it more powerful than the OS kernel or even the hypervisor. Now, when you run in SMM, you have some special superpowers. So, for example, you have full access to all the physical memory of the machine, but the other way around is not true, meaning code running outside of SMM can't read or write your data. Other such superpowers include the ability to read and write all the MSR supported by the platform, and also the ability to write the BIOS region found on the SPI flash memory, which basically means you can do a firmware update using this mode. So in a typical attack scenario, our goal would be to elevate our privileges to ring -2, that is SMM. One assumption we are going to make is that we are already running with ring 0 privileges, so that is kernel mode. And the reason we make this assumption is that it lets us freely issue software SMIs, and that's going to make our life a bit easier. So the attack vector we are going to use is what is known as a confused deputy attack against SMM. So basically we are going to trick the privileged SMI handler in order to corrupt or otherwise modify the contents of SMRAM in unexpected ways. Combined into a full attack, we will begin by first hunting down these SMRAM corruption vulnerabilities, exploit them in order to actually corrupt memory. Using the memory corruption, we will slowly build stronger and stronger primitives until we eventually manage to hijack control flow. And finally, we can run our payload, which can be anything from installing a very stealthy SMM backdoor, maybe reflashing the BIOS in order to gain persistence, or maybe just infecting the hypervisor or any nested or any VM it currently hosts. Still, for the duration of this talk, we are only going to focus on the first part, that is hunting down the vulnerabilities. So to effectively hunt down the vulnerabilities, we have to analyze the potential attack surface. So if you remember in the first part, we went through the process of invoking an SMI from a UEFI environment. But the truth is, we can simply replicate all these steps from a live operating system long after the boot process has finished. And luckily for us, we don't even have to do all these steps ourselves, because chipsec already has a built-in command for it. So this command receives a lot of parameters. The most important ones for our discussion are the GUID identifying the handler we want to call, the address of the communication buffer in physical memory, and the contents of the communication buffer. So these three parameters together form the basis of what would be our attack surface. Now, since the firmware wants to protect SMRAM against corruption, there are obviously some restrictions to that. So one obvious restriction is that the communication buffer cannot overlap with SMRAM, because if that wasn't the case, corrupting SMRAM memory would be a trivial task. Now, in order to enforce this, the SMM entry point calls a function called SMM is buffer outside SMM valid to make sure the CommBuffer does not overlap with SMRAM in any way. And if this check fails, the SMI simply returns an access denied status to the caller. Now, some poorly written SMI handlers may allow you to sometimes bypass this restriction, and with that in mind, let's go on to the first backlash. So here I have a really simple SMI handler. You can see that all it does is reading some MSR, computing a 64-bit value out of it, and then writing the result into the communication buffer. Now, notice that while doing so, the handler implicitly assumes that the communication buffer is at least 8 bytes long. But unfortunately, this check is not enforced explicitly anywhere in the code. So let's see how an attacker can exploit this condition. So in order to exploit this condition, the attacker would like to place the communication buffer in a memory location as adjacent as possible to the base of SMRAM. So in this particular case, we set it to be SMRAM base -1 and set the respective size to be just 1 byte. Now the attacker will move on to trigger the vulnerable SMI, but first the SMM entry point will be called. It will validate using SMM is buffer outside SMM valid that the CommBuffer does not overlap with SMRAM. And since technically it doesn't, this check will be successful and the actual handler will be called. Now, even though the size of the communication buffer is just 1 byte, the handler will completely ignore this and just blindly write a keyword value into it. And by doing so, it will also going to corrupt the lower 7 bytes of SMRAM, which is definitely a bad thing. So the mitigation for this is pretty simple. Basically, the handler should always explicitly check the size of the communication buffer and not make any implicit assumptions about it. If the size of the header, size of the buffer, if the actual size differs from the expected size, the handler should just bail out without doing anything. So the bug that I just showed you has some obvious limitations. The most important one is that we don't control where the corruption takes place. We're pretty limited with that. And if we want to find a stronger primitive, we should be looking for other types of vulnerabilities. So here I have the second SMI handler, and this one begins by taking the first field out of the communication buffer and treating it as some kind of an operation code that tells the handler what it should do next. And we can see that the valid values for this opcode field are either 0, 2, or 3. And if the actual value differs in some way, then the default clause will be executed. And the default clause is pretty interesting because it takes the second field out of the CommBuffer, interprets it as a pointer, and then writes a status variable to the pointed memory location. So in order to exploit this condition, the attacker would first craft a communication buffer, write it to a location in physical memory accessible to him that is outside of SMRAM, and then, just like before, we'll move on to trigger the vulnerable SMI. The SMI will first inspect the operation code field to determine what it should do next, but since this field is under the attacker's control, he can choose an invalid value and therefore force the handler to go into the default clause. In the default clause, the handler will fetch an address out of the CommBuffer and write to the pointed memory. And since this address field is also under the attacker's control, he can choose an address that resides in SMRAM and therefore cause corruption. So the moral of this story is that SMI handlers must always validate pointers that are nested within the communication buffer. And to do so, they can just call the SMM is buffer outside SMM valid function that we are already familiar with. Sometimes, even calling SMM is buffer outside SMM valid on nested pointers is not enough to make the handler fully secure. So this is a snippet from the third SMI handler. And this one begins by copying a certain field from the CommBuffer into a local variable in SMM. And since the developers were security aware, they validate this pointer using SMM is buffer outside SMM valid. And if this check passes, they feel confident enough to copy some memory to the pointed location. Now, the crux in identifying this vulnerability is to notice that while the call to SMM is buffer outside SMM valid is done using the local variable in SMM, the call to copy mem is done using the field value which is fetched again from the CommBuffer. So there is actually a double fetch issue here that might be subject to a time of check, time of use attack. So in order to exploit this condition, the attacker would first write the communication buffer to memory, and at this point, the pointer field is safe, meaning that it points to an object outside of SMRAM. And then, just like before, the SMI handler will be invoked. One of the first things it's going to do is copy the field from the CommBuffer into SMRAM. And at this point, both pointers are synchronized, meaning they point to the exact same object in memory. Now, the call to SMM is buffer outside SMM valid is made, and since the pointed object resides outside of SMRAM, it will be completed successfully. Now, an important thing to understand is that SMM wasn't designed with concurrency in mind, so that means that while one CPU is busy servicing the SMI interrupts, all the other CPUs are going to enter SMM and wait for the first one to finish. So that means the attacker can't utilize any of the other CPUs present in the system in order to modify the contents of the CommBuffer. But it is still possible for an I/O device to perform DMA operations on main memory. So that means a DMA attack can simply change the contents of the communication buffer while the handler is executing, and more specifically, we can make the pointer field point somewhere else inside SMRAM. Now the handler will continue executing. It will fetch again the pointer from the CommBuffer and pass it as the destination argument to a copy mem operation, and by doing so, it is going to corrupt some SMRAM memory as well. So in order to prevent these issues, we should follow some simple guidelines. Basically, double fetches from the CommBuffer are considered to be dangerous, and if the CommBuffer contains any sensitive field, such as pointers, they must be copied into local variables in SMRAM, and from that point onwards, only the SMM local copies should be used. So now let's move on to the third and final part of the talk, where we will talk about a small tool we wrote called Brick. So simply put, Brick is a static automated analysis tool that lets you easily hunt down some of the SMM vulnerabilities that we just talked about. This tool is primarily based on IDA, and basing it on IDA gives us two significant advantages. So the first one is that we gain access to a really vast and rich ecosystem of different tools, scripts, plugins, and so on. So we can leverage these third-party tools in order to solve a lot of the challenges we are facing. And the second one is that we gain access to the hex-raised decompiler, which means we can do all our analysis in a much higher level. So instead of searching for vulnerabilities by analyzing assembly instructions, we analyze the decompiled pseudocode and its associated AST and so on. And now let's move on to a quick demo I prepared. Okay. So here I have a directory with 4 SMM binaries. So of course, if I want to scan them for vulnerabilities, I can do it manually. But the problem with a manual approach is that it's not scalable in any way, and that wouldn't be feasible if the directory contained, for example, 40 modules. And that's exactly where Brick comes into play. So instructing Brick to scan the directory is just a matter of running this really simple Python command line. So let's run it and see what happens. So basically right now, all the images were opened up in IDA, and after the initial auto-analysis is complete, we move on to the second phase where we run a bunch of heuristics in order to pinpoint the potential vulnerabilities. And we should be done in a couple of seconds, hopefully. We're already done, so sorry for that. Okay, so yeah, once Brick finishes scanning the directory, it is going to output all its findings in an HTML report. So let's open up this one and see what the findings are. Can everyone see the font? Okay, so the output of this tool is a bit dense, and it does take some time to be able to interpret it efficiently. But the general rule of thumb is that you should always start by looking at the lines highlighted in red, because these are the potential vulnerabilities that were spotted with the most accuracy. So in the first SMM image, we can see Brick managed to spot an SMI handler that does not check the size of the CommBuffer, and therefore it suggests we will check it to see if we can make it somehow overlap with SMRAM. So let's open up the associated IDB. Okay, so here we have a really simple SMI handler. We can see that all it does is comparing the first field of the CommBuffer against some magic signature, and if the signature matches, some function gets called, and the result is immediately written into another field in the CommBuffer. Now notice that indeed the size of the CommBuffer is not referenced in any meaningful way, and that means that if we manage to place the CommBuffer just below SMRAM, this field access here will actually corrupt SMRAM memory. So that's actually a pretty good corruption primitive. Now, the second SMM image suffers from another issue. We can see there is a certain handler that fetches the same field twice, and therefore Brick tells us that this might be subject to a time of check, time of use attack. So let's validate this finding also. Okay, so indeed we can see field 18 is being fetched twice. And now just to make analysis a bit easier, let's rename this one here to be field 18A, and let's rename this one to be SMM field 18B. And notice that while the validation using SMM buffer outside SMM valid is done using SMM field 18B, the call to the following function at 9FC is done using field 18A. So that means that in a potential attack, we can issue this SMI with field 18 pointing to SMRAM memory. This value will be saved into field 18A, and just before it is being fetched again into SMM field 18B, a DMA attack can modify the original field in the CommBuffer to point to a supposedly safe location outside of SMRAM. So that will make the validation at SMM buffer outside SMM valid to be successful, and function 9FC will be called with a pointer argument pointing to SMRAM, which is unexpected. So under the hood, we can see this function is basically a wrapper around copy mem. So once again, we managed to find a cool memory corruption primitive. So the third image has an SMI handler that suffers from two distinct issues. One of them we already saw, the handler that does not validate the size of the CommBuffer, but this one also does not validate pointers that are nested within the communication buffer. So let's open up the IDB. So once again, a really simple SMI handler. The logic here is really minimal. What this SMI handler does is taking the first field out of the communication buffer and simply copying it into a local variable called buffer. Notice that indeed no validation over this field takes place, which means we can set the global variable to any address we would like, including addresses in SMRAM. To determine whether or not we can actually exploit this, we should be looking at the places where this buffer variable is consumed. So let's very briefly go to one of the xrefs. So in this function, we see a buffer is being forwarded into yet another function with some constant integer. And this function under the hood will basically just zero down the entire memory range. So also a pretty powerful memory corruption primitive. Now, the fourth and last module, we get some different result. This one seems to be completely resilient to all the attacks we just described. And actually, that shouldn't come as a surprise, because if you see here, Brick tells us that this module actually comes from EDK2, which is the reference implementation of UEFI. And generally speaking, the code quality of the reference code is much higher compared to the code written by the BIOS vendors and the OEMs. Sorry. Yeah, I accidentally closed the slide deck. Okay, so after we saw Brick in action, let's talk a bit about how the tool works under the hood. So when running Brick, we have 3 different phases. First, we have the harvest phase, followed by the analysis phase, and finally we conclude with a summary phase. So in the harvest phase, we basically give Brick some input object that somehow encapsulates the SMM binaries we want to scan. So in the demo, that was just a plain directory, but that can also be a more natural object, such as an SPI dump, a UEFI capsule update, maybe an entire BIOS image you downloaded from the vendor's website, and so on and so on. Then Brick will leverage some third-party tools, such as a UEFI extract or a library known as the UEFI firmware parser, in order to extract all the SMM images, and then it will just dump them to a dedicated directory. Next comes the analysis phase. So in this phase, each SMM image is opened up in IDA, and after the initial auto-analysis is complete, each image goes through a set of different modules. So these modules are basically divided into 3 categories. First, we have the processing modules, which merely do some processing over the IDB. Then we have the analysis modules, which are responsible for detecting and pinpointing potential vulnerabilities. And finally, we have informational modules that emit some valuable information which isn't necessarily related to vulnerabilities. Now, doing this entire process sequentially would obviously take large amounts of time. And therefore, in order to speed things up, we use a tool called IDAHunt. And IDAHunt lets us spawn a number of concurrent IDA instances, and therefore, by parallelizing the entire process, we make it much shorter. So each Brick module is under the hood implemented just as an IDA Python script. But since the API of IDA Python can be a bit rough at times, we don't use it directly, but rather use a higher level framework called BIP. And now, like I said, the modules themselves can be divided into 3 categories. The processing modules are mostly in charge of resolving some of the shenanigans of UEFI, such as the different service calls, locating some of the global variables, and so on. And these modules are mostly based on a plugin called EFI Explorer. The informational modules let you determine if the image uses UEFI legacy protocol, or whether or not it comes from a reference implementation such as EDK. And finally, the detection modules are actually in charge of locating the vulnerabilities. So we have 1 module per vulnerability class. And all of these modules are implemented using pretty simple heuristics. So just to get you a glimpse of what a heuristic looks like, let's take a look at the code responsible for detecting the usage of unsanitized nested pointers. Basically, we iterate over all the SMI handlers installed by the image, and then for each SMI handler, we check to see whether or not the communication buffer is consumed in any way. If it is not, we can assume the handler is implicitly safe and just move on to the next one. If, on the other hand, the CommBuffer is being utilized, we start to recursively scan the AST associated with the function, and we are only interested in nodes that represent calls to other function. And for each such node, we ask to see whether the destination function is SMM is buffer outside SMM valid. So if we manage to find such node, we assume the handler knows what it is doing, and we mark it as safe. But if on the other end no such node is found, we conclude that the handler simply misses some critical validation, and therefore we flag it as potentially vulnerable. But the heuristic I described so far is a bit oversimplistic. And the reason for it is that a particular handler might not call SMM is buffer outside SMM valid, simply because the communication buffer does not hold any nested pointers, but rather other data types such as integers or Boolean flags and so on. So if we want to make detection more accurate, we have to figure out the internal layout of the communication buffer. And in order to do so, we use yet another plugin called the Hexrays Code Explorer that lets us reconstruct the structure of the CommBuffer, and if we see that the reconstructed structure holds members which are pointers by themselves, that greatly boosts the confidence we have in the detection. So the modified heuristic basically remains the same, only takes this structure reconstruction thing into account. So having really simple heuristics has a lot of advantages. So they are easy to read, to write, to maintain, and so on. But that also means we are going to suffer from some false positives and false negatives as well, because the world is more complicated than how we usually describe it. So when it comes to false positives, so it's important to understand that Brick is mostly a helper tool. It's not going to replace a human analyst, and eventually a human analyst is required to determine if a particular result is true or not. And that means that as long as we keep the rate of the false positives below a certain threshold that is manageable by a human being, that might be good enough. And when it comes to false negatives, it's important to note that the main use case of running Brick is not scanning individual SMM images like we did in the demo, but rather scan an entire BIOS image with the intention of ultimately being able to compromise SMM and through that the entire machine. And in order to do so, we don't necessarily have to find each and every vulnerability present in the BIOS, but just finding a handful of them might be enough. So a bit about the results we got from this tool so far. So actually this slide is already out of date. It's not 2 CVEs, we already have 3 CVEs using this tool. So 2 are from Lenovo and 1 from Asus. We also have about a dozen of other vulnerabilities that are stuck somewhere in the responsible disclosure pipeline. So that means I can't say the names of the affected vendors, but I can say that the list basically includes almost all the well-known names and OEMs you are familiar with. And some of these bugs also affect parts of the reference code which is shared between multiple vendors. So that means some of them have a broader impact. So to summarize, I'll say that in my humble opinion, Brick is a very promising tool, but it's also a really young project. So that means there is definitely a lot of room for improvement. So here I wrote down some critical areas for future revisions. So one thing would be adding more detection modules to help pinpoint bug classes that currently just go below our radar. Also, we need to improve the reliability of the existing detection. So that means lowering down both the false positives rate as well as the false negatives rate. The third critical issue has to do with the performance of the tool. So like you saw in the demo, scanning 4 SMM images might take about 1.5 minutes, but scanning an entire BIOS image can take up to an hour. So there's definitely some room for optimizations there. And that's exactly where you can make an impact, because Brick is already an open source tool available on GitHub. So if you're interested in SMM or firmware security in general, feel free to contribute in any way you see fit, either by opening up issues, submitting pull requests, and so on. And with that in mind, I want to thank you very much for your attention and wish you an interesting and fruitful conference.
So do we have any questions? Several.
Thanks for the very interesting presentation. It was very useful. I had a question regarding one of the checks, which checked if a node had access to a function called isOutside SMM CommBuffer, I think.
You're talking about this one?
Yes. So from what I understand, you decide that a function is okay if it calls that other function, right? Or that node is okay if it calls the other function.
Yeah, so an SMI handler is assumed to be safe if it calls SMM outside, is buffer outside SMM valid, and if the first argument passed to this function is not the CommBuffer itself. So there is basically a distinction between two things. You can verify that the CommBuffer itself does not reside in SMRAM, and any other value that you pass to this function is assumed to be like a nested pointer or something like that.
Okay, but if there is, for example, an off by one issue there, this would not catch it, right?
So, like I said, so most of these heuristics are quite simple. There are probably there are some, false positives and false negatives alike. So these heuristics basically, they detect the most common misuses or bad practices that are present in SMM images, but they don't cover all the cases.
Okay. Yeah, thank you.
So you said Brick is public and a bunch of vulnerabilities are still going through disclosure. So if I download this today and run it on some OEM, I'm going to get 0-day vulnerabilities, right?
I don't think I heard the question.
So Brick is public, and you said you have a bunch of other vulnerabilities that you haven't listed the CVEs for because they're still going through the vulnerability disclosure pipeline. So if I download Brick today and I run it on an OEM, I'll probably find some 0-day vulnerabilities, correct?
Yeah, so from our experience, almost any firmware image that we downloaded and scanned had some issues. Very few vendors managed to pass all the tests without any major finding. I will say that not necessarily all vulnerabilities are exploitable. For example, in the first bug class, you are very limited in where the corruption takes place. And I think that it would be really rare to be able to perform a full attack cycle using just this vulnerability. You might be able, to get a denial of service or something like that, but probably it won't be enough to get code execution.
Sure.
Yeah, so I had a question regarding time of check, time of use. Mm-hmm. So you said you could use DMA in order to change the value in between readouts. So my question is, have you actually tried this in practice? Because my logic tells me that this value is then cached in the CPU.
So I'll be honest and tell you that I haven't tried this myself. So this was, mostly things that I read about. So I don't know if that's, actually exploitable. So maybe there are, some, issues with the cache or something like that prevents you from doing it. But if you go through the EDK documentation, they will specifically mention that doing double fetches from the CommBuffer is something dangerous and might lead to a time of check, time of use attack. So I mostly based my work on reading the EDK documentation.
Okay, thank you.
Any other questions? Okay, so thank you. Great. Okay.